Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer the next questions from sample paper number 3, RK Bali Navigation Book. This is the 4th edition book. Even if you tend to have any other edition book, don't worry, the questions are going to remain the same. Even if you take 5th edition book, the 6th, the 7th, the questions in the sample papers are the same. So let's start with question number 11. Aircraft departs from position A, flies northward following the meridian for 2750 miles. It then flies westward along the parallel of latitude for 400 miles. What are the new coordinates of position Bravo? So let's plot this. We are in the southern hemisphere, right? So let's say this is your Earth, this is the equator. 9 degree 10 minutes south, 9 degree 10 minutes south, 178 degree 22 minutes west. This is your starting position, point A. From this point A, you are going to fly for 2750 nautical miles. So I am also going to represent this Earth on this horizontal paper. Okay, for better understanding. Okay, so your point is A, somewhere here. 9 degree 10 minutes south, 178 degree 22 minutes west. And now you fly 2750 nautical miles northward. 2750 nautical miles northward. So when you fly northerly or southerly direction along a fixed longitude, you actually fly a great circle distance, which is d lat in degree into 60. So 2750 nautical miles equals to d lat in degrees multiplied by 60. So d lat in degrees will be 2750 divided by 60. 2750 divided by 60 equals to 45 degree 50 minutes. 45 degree 50 minutes. So that is your difference in latitude. This difference in latitude is between the initial latitude and the final one. So initial is 9 degree 10 minutes south. You are going to fly up to the equator. So from 9 degree 10 minutes south to the point of equator, the d lat will be 9 degree 10 minutes. So out of total 45 degree, a total of 45 degree 50 minutes, 9 degree 10 minutes traveled in the southern hemisphere, from traveling from point A to the equator. Now what is the remaining d lat? So 45 degree 50 minutes minus 9 degree 10 minutes is 36 degree 40 minutes. 36 degree 40 minutes. So remaining d lat of 36 degree 40 minutes will be traveled in the northern hemisphere. Will be traveled in the northern hemisphere. So your new latitude is 36 degree 40 minutes north. Longitude remains the same, 178 degree 22 minutes west. 178 degree 22 minutes west. Now from this new position, you fly west along the same latitude for 400 miles. Now I am going to draw another diagram. So for Ramline distance, you draw a diagram that I have always taught you to draw one. So you draw the Earth diagram from the perspective of North Pole. So 0 degree prime meridian, 180 degree east and west, anti-meridian 90 east, 90 west. Okay. So the first longitude is 178 degree 22 minutes west. 178 degree 22 minutes west. You are flying in westerly direction. All westerly directions are clockwise when viewed from the top of the North Pole. So you are going to fly in this direction like this. So now you may D, your new position, your destination may be in the western hemisphere. If D long is less than 1 degree, if D long is more than 1 degree, 2 degree, you will enter a new hemisphere, the eastern hemisphere, and your new longitude will be somewhere near 180 east longitude. So let's find drumline distance given is 400 nautical miles. Drumline distance is 400, D long in minutes into cos of latitude. What latitude? We are flying on latitude 36 degree 40 minutes north. So what we are doing is we are actually flying in westerly direction from this point. So we are flying westerly like this, like this. So 36 degree 40 minutes, cos of 36 degree 40 minutes. So D long in minutes will be equal to 400 divided by cos of 36 degree 40 minutes 0.8. So 400 divided by 0.8 is 500 minutes. 500 minutes is 8 degree 20 minutes. 8 degree 20 minutes. So your new longitude will be old longitude plus the D long between them. Old longitude is 178 degree 22 minutes west. Now total D long is 8 degree 20 minutes. Now the D long between 180 degree west and 178 degree 22 minutes is 1 degree 38 minutes. 1 degree 38 minutes. Total D long is 8 degree 20 minutes. So out of that 1 degree 38 minutes will be traveled in the western hemisphere from 178 degree west up to 180 degree west. Now remaining D long is 6 degree 42 minutes. So that 6 degree 42 minutes will be traveled in the eastern hemisphere. 6 degree 42 minutes. So your new longitude will be old. So it will be, I'm correcting this, it will be 180 degree east longitude minus this D long 6 degree 42 minutes minus D long 6 degree 42 minutes. So 178 degree 22 minutes minus 6 degree 42 minutes is 171 degree 40 minutes east. So your new longitude is 171 degree 40 minutes east. So your new position of Bravo will be same latitude 36 degree 40 minutes north and 171 degree 40 minutes east. So option Bravo is the correct answer. Okay. 36 degree 40 minutes north, 173 degree 19 minutes east is what they have got. I have got 171 degree 40 minutes. So the closest is option Bravo. Next. Position A is given to you. Position B is given. Distance between them is given. Bravo is to the east of A. Okay. What is the longitude of position A? So let's draw this diagram. This is 0 degree prime meridian. Position B is 45 north, 45 degree 15 minutes east. 45 north, 45 degree 15 minutes east. Position A is to the west of it. Now position A can be in the same hemisphere, so it can be somewhere here, or it can be in a completely different hemisphere here. So we don't know that. We will find that out. Now both are located at same latitude but different longitudes. So that means we have to find drumline distance. Drumline distance is D long in minutes into cos of latitude. What is distance given? 200. Cos latitude is cos 45. That will be equal to D long in minutes. So d long in minutes will be cos 45 0.7. So 200 divided by 0.7 is 285.7 minutes, or approximately 286 minutes. That will be equal to 4 degree 45 minutes. That is your d long. So position A longitude will be position B longitude minus, because when you are you are at position B and in the eastern hemisphere, when you travel westerly direction, the values of longitudes will decrease up to prime meridian. So 45-degree east, 40-degree east, 39 east, 38, 37, so on and so forth. The values will go on decreasing up to prime meridian 0 degree. After that, beyond that, the longitude values will start increasing in the western hemisphere, 10, 20, 30 west, 40 west, so on and so forth. So here we will have to subtract d long. So 45 degree 15 minutes is minus d long 4 degree 45 minutes. So 45 degree 15 minutes minus 4 degree 45 minutes is equal to 40 degree 30 minutes east. So your new position is 45 north and 40 degree 40.5 degree east. Okay, so that means position A is in the same hemisphere as position B. So correct answer is option Charlie. Closest answer is option Charlie. 40 degree 32 minutes east. Now this is a very important question. It gets asked in ATPL exams also. Two aircraft are flying eastwards. Aircraft A flies along 45 north latitude. Aircraft B flies along the equator. If aircraft A is flying at speed of 300 knots, what would be the speed of aircraft B if both aircraft fly around the earth in the same journey time? So that means there are two aircraft, both are flying at different latitudes. Okay, and we have convergency of meridians. So the first latitude given is 45 north parallel of latitude. 45 north parallel of latitude. The second latitude given to you is the equator. Now, let's start with 45 north parallel of latitude. The plane on 45 north parallel of latitude will be flying easterly direction, make a complete 360-degree rotation around this parallel of latitude. So when it makes this complete 360-degree rotation, it covers a distance called Rammline distance. Why Rammline distance? Because you are flying at same parallel of latitude between two different longitudes. The starting longitude is the same and the final longitude when you complete 360-degree rotation is also the same. So d long, or the difference between these two longitudes, will be 360 degree. So Rammline distance is d long in minutes into cos of lat. So d long is 360 degree multiplied by 60 into cos 45. So cos 45 into 360 into 60 is 15273.5, 15,273 nautical miles. Speed is given to you 300 knots. Time taken, the journey time will be distance by speed. So 15,273 nautical miles divided by 300 knots will be equal to 50 hours 54 minutes. 50 hours 54 minutes. Now, second example, second situation. Another aircraft is flying, aircraft B is flying along the equator, same 360 degree but at equator. And it is completing that journey. The journey time is the same journey time taken by the first aircraft. The first aircraft took a journey time of 50 hours 54 minutes. So the second aircraft encircling the earth at parallel of latitude 0 degree north south will also complete this 360-degree rotation in the same journey time of 50 degree 54 minutes. So let's apply Rammline distance. We have to find out speed. So let's first find out drumline distance, which is d long in minutes into cos of lat. So again 360 into 60 into cos lat 0. So 360 into 60 is 21,600 nautical miles. Time is the same, 50 hours, 54 minutes. So speed will be distance by time. The speed will be more than 300 knots, right? Because it has to cover more distance, longer distance, much more than 15,000 is 21,000. So it has to cover much more distance in the same journey time. That is only possible when this aircraft will be flying at a ground speed of more than 300 knots. And if you look at the options here, all options are more than 300 knots, so you cannot eliminate anything. But if there is any option which is less than 300 knots, eliminate it straight away. Okay, and then so that increases your chances of success. But otherwise, distance is 21,600 divided by 50 hours, 54 minutes. That is 424 knots. 424 knots. Option brown. Question 14. When correcting rectified airspeed, which is calibrated airspeed of 150 knots, you get a true airspeed of more than 150 knots. Why is that so? Okay, now at ISA conditions, in ISA conditions, okay, when you're flying under ISA conditions, your calibrated airspeed becomes equal to your true airspeed. Okay, but in this case, your true airspeed is much more, it's not only equal to calibrated airspeed, but more than that, more than calibrated airspeed. Now, all your pressure instruments, all your aircraft is designed to perform in ISA conditions. Your aircraft will produce maximum of best performance parameters or performance numbers when it is flying in ISA conditions or conditions which are better than ISA. So in this case, in ISA conditions, your task must be equal to your CAS. But as given in the question, it is better than CAS. It is more than calibrated airspeed. That means your aircraft is flying in ISA conditions or conditions better than ISA. That means option A will be the correct answer. Density of air is greater than the ISA mean sea level density expected to be found at mean sea level. Okay, so if density at mean sea level is much more than ISA density, what ISA says or ISA requires, that means your density more, that means more air going through your engines, more density air, that means more pressure, and therefore your aircraft performance will increase. And as a result of that, that performance will be reflected in your airspeed, your true airspeed. Therefore, option A is the correct answer. Density of air must be greater than the ISA mean sea level density. Question 15. What is the purpose of a compass swing? Now we all know that compass deviation is the angle between magnetic track and compass track, right? Deviation is a quantity that links magnetic and compass directions, the connecting link, the joining link between magnetic and compass. So why we do this compass swing? The compass swing is performed to curtail the deviation errors. Now we all know that your compass direction that you will be actually flying in the air will be much different than the magnetic direction because of local electrical influences in your cockpit. Now, efforts are made, trials are done, attempts are made to curtail this deviation error or to bring compass direction as close as possible to magnetic direction. And that procedure is called compass swinging or compass swing. It is done to observe and determine deviations, then to correct or remove as much deviations as possible. Perfection is not possible, so we aim for excellence to record the residual deviation. So after removing whatever deviation that is possible to be removed, whatever deviation is left behind, that is called residual deviation. So that is your compass finger. It decreases the space or the margin of error between your compass direction and magnetic direction. And then whenever you fly, you will observe in your cockpit below the magnetic compass, you will have a card called this compass correction card, and you will see headings displayed. So if you want to fly northerly direction, 360, because of deviation in existing in that particular aircraft, you will have to fly a heading of uh, 350, 340, 355, whatever is written in the box below this. Now, in this case, it's written if you want to fly northerly direction, fly 360. That means if you want to fly a northerly direction, there will be no deviation error. If you want to fly 360, fly a heading of 360 and you will fly along that direction. But next column says if you want to fly a heading of 030, you turn your aircraft heading to a heading of 029er. So difference between 30 and 29 is 1 degree. 1 degree deviation error. So that means if you want to fly a heading of 030, in your particular aircraft you will fly a heading of 029er. Flying a heading of 029er is nothing but or is like flying a heading of 030. Okay, so you will have to follow this compass card directions and fly your aircraft accordingly. And this happens because of deviation, the phenomenon of compass deviation, and compass swinging is done, and that deviation error is minimized as possible. And then the final result is displayed in the form of a compass correction card. So the purpose of a compass swing is to confirm align lubber lines with true north, confirm accuracy of Schuller tuning, align compass north with magnetic north. Yes, like I said, swinging is done to bring compass north and magnetic north close together, as close as possible to each other, decrease the difference or the error magnitude between them. So option C. Question 16. There is a runway in the north hemisphere and agonic line. Agonic line means zero variation. So that means your true heading will be equal to your magnetic heading. 045 true heading is equal to your 045 magnetic heading. If aircraft with zero compass deviation, so in addition to that, there is another advantage. Your aircraft does not have any compass deviation error. Now, if this aircraft takes off in still air, means it will take off from the runway in the direction of 045, what will the northerly turning error be? Okay, so let's draw this diagram. So this is the north datum. There is a runway oriented 045. So let's say 040,220. Now if your aircraft takes off from this runway 040, what will it do? It will accelerate and then lift off and then fly a heading of 045. Fly a heading of 045. So what will the error be? What will the compass error be? Will the compass show the accurate direction of 045? Will it show any other direction less than 045, let's say 040, 035, or any direction more than 045, 050, 055, whatever? So remember, our magnetic compass is subject to two kinds of errors, turning errors and acceleration deceleration error. Now in this case, acceleration deceleration error applies because you are accelerating your aircraft on a heading of 045. Now another very important point, acceleration errors or deceleration errors happen to exist on easterly and westerly headings. Now in this case, we are not strictly flying a heading of easterly or westerly. We are flying 045, which is midway between north heading and east heading. But still the magnetic compass will tend to show or will get influenced by this acceleration deceleration error, and it will show some inaccurate direction. Now what happens is when accelerate you accelerate on an easterly heading, the magnetic compass will not show accurate 090 direction. If you are flying along easterly heading, you should get shown a heading of 090, but the magnetic compass will show a direction of less than 090, 075, 080, depending on your acceleration, magnitude of your acceleration. In simple words, your magnetic compass will tend to point towards northerly direction if you accelerate your aircraft in the northern hemisphere. So in this example, in this question, we are also accelerating an aircraft in the northern hemisphere, but on a different heading of 045. So again, under the influence of acceleration error, this magnetic compass will show a heading towards northerly direction. That means it will show any heading less than 045 tending towards northerly direction. Less than 045. So correct answer is option Bravo. Next. Question 17. In order to convert true heading into magnetic heading, you require a compass card and dash. So you require a compass card like this, okay, and you required a map with isogonal lines. Now we all know that magnetic variation is the connecting link between true direction and magnetic direction. And how will you get to know the value of the magnetic variation of the location you are flying at or in the airspace you are flying? Sectional charts. Now, this is a VFR visual flight rule sectional chart. Similarly, you can find IFR charts. And in these charts, they show isogonal lines are depicted on these charts. So in this particular example, you can see this red color dashed lines and 7 degree west written. So 7 degree west means if you are flying in this particular airspace somewhere here, you will apply a magnetic variation of 7 degree west to your true direction. So uh, correct answer is option Charlie. To convert true headings into magnetic, you require a compass card and map with isogonal lines depicted. The rollout must be performed at dash heading when you turn your heading from northwest to southeast in the south hemisphere. So now, like I said in the previous question, the magnetic compass is subject to two different errors: turning errors along north headings and south headings, acceleration deceleration errors along east headings and west headings. So now here we are going to explore turning error in the southern hemisphere. Okay, we will focus our attention to the on the southern hemisphere. This is the south hemisphere. This is north. Now northwest direction. This is north, south, east, and west. Northwest direction is 315 and southeast direction is 135. So that means you want to turn your heading from a heading of 315 to a new heading of 135. There are two ways you can do this. You can turn your aircraft through the north pole like this clockwise, or you can turn your aircraft anti-clockwise through the south pole. Now turning errors, there will be two possibilities. We will explore both of them. Possibility number one, let's say you turn your aircraft in anti-clockwise direction. You turn your aircraft from northwest direction to southeast direction anti-clockwise. That is through the south pole. Now when you do this, that is you are in the south hemisphere, and second condition, your turn happens through the south pole. In such case, the result will be, in such case your magnetic compass will be sluggish. So you are in the south and you are also turning through the south pole. The magnetic compass will be sluggish. It will lag behind. Sluggish means it will lag behind. Okay, it will be running slow. So solution to this problem. So that means once you have completed your turn from heading 315 to a new heading of 135, the magnetic compass should show the new heading 135 accurately. But in this case, because the magnetic compass is sluggish, it's lagging behind, even after achieving a new heading of 135, the magnetic compass will tend to show any heading which is less than 135. Let's say 130, correction, any heading which is more than 135. So you're turning from 315 like this. Okay. So it will show any heading like 135. So more than 135, my bad. 140, 145, 150, whatever. Okay, but it won't show accurate heading of 135. It will show any heading different from 135 because it is behaving sluggish. Okay, it is sluggish, it is lagging behind. So the solution will be, you will not trust this magnetic compass because you know it's sluggish, it's lagging behind. So you, instead of trusting this magnetic compass, you estimate, you make your own estimate, your own predictions, and you start rolling out your aircraft. You start rolling out your aircraft much before, much before your desired heading, in this case 135, is achieved, much before your desired heading is achieved. So if you wait till you get to heading of 135 and then roll out your aircraft, okay, you will actually land up at some new heading. One less than 135 means 120, 110, something like that. Because magnetic compass is sluggish, and if you trust that blindly, and after you roll out your aircraft on a new heading of 135, your magnetic compass will actually point towards heading of 120, 110. Once it loses its sluggish behavior and catches up. Okay, so you will have to anticipate and start rolling out much before your desired heading is achieved. So by the time you complete your rollout, your magnetic compass will catch up and then show you the correct accurate heading, 135 or any heading around that. So that is what happens when you are in the south hemisphere and you turn your aircraft to the south pole. Second situation is, you are in the south hemisphere. Okay, you are in the south hemisphere, but you turn your aircraft around the north pole, so that means instead of flying anti-clockwise direction like this, what will you do is, you will fly a clockwise direction, around the north pole and then get to southeast direction, so in such case the result is that your magnetic compass is overactive. Okay, it will run ahead of you. You may be turning your aircraft moderate pace at a steady standard rate turn, but your aircraft magnetic compass will show you a rate of turn more than the standard rate. Okay, it will be overactive. So the answer or the solution to this problem is that you start rolling out your aircraft much later, much later after passing your desired heading. Okay, in this case, your desired heading is 135. So you know your magnetic compass is overactive. Okay, you won't trust that magnetic compass. So when you achieve a new heading of 135, then magnetic compass shows a heading of 135. You won't start rolling out your aircraft at that time. You will start rolling out your aircraft much later at a new heading of, let's say, 140 or 145, something like that. Because you know magnetic compass is overactive, it will show you that you have achieved a heading of 135 even when you have not achieved it. Okay, so it's an illusion. So you start rolling out 140, 145, any heading more than that. So by the time you roll out at 140, 145, your magnetic compass will have achieved a correct accurate heading of 135, which is your goal, which is your main desired heading. So any heading more than 135. Okay, so 140 or something like that. And if you are turning through the south pole, again you will start rolling out before your desired heading. So before your desired heading means again 140, 145, whatever. Okay, so whatever direction you choose to turn, clockwise or anti-clockwise, the value is going to be around 140 something. So correct answer here is option bravo, 145. Question 19. Approximately how many nautical miles correspond to chart distance 12 centimeter and scale is given to you. So scale equals to a chart distance divided by earth distance, right? So a chart distance is 12 centimeter. Earth distance you do not know. Scale is 1 divided by, so earth distance will be 12 multiplied by, cross multiply. So you will get an answer in terms of 24 into 10 raised to 6 centimeter. Earth distance is always in nautical miles. So we have option Bravo, which is 130 centimeter. That is entirely wrong. It is 24 into 10 raised to 6 centimeter. So convert centimeter into corresponding nautical miles. What you will do is 1 nautical mile is 1852 meter into 100 centimeter. So 24 into 10 raised to 6 centimeter will be equal to how many nautical mile? Cross multiply. 24 into 10 raised to 6 divided by, so 24 into 10 raised to 6 divided by 1852 into 10 raised to 2. So 24 in divided by 1852 into 10 raised to 1, 2, 3, 4. So 120, final answer will be 129.58 nautical miles. So 129.58 is approximately 130 nautical miles. This is nautical mile, not millimeter. It is nautical mile. Next, a straight line on a Lambert's chart for normal flight planning purpose is what? Now, a straight line can be a meridian, or if it's not a meridian, it will be approximately a great circle. So remember all the properties of Lambert's chart. So a great circle will be equal to or somewhat equal to or almost equal to, or it will tantamount to a straight line on a Lambert's chart if that great circle happens to be anywhere near the parallel of origin. So option A is the correct answer. So this concludes the lecture. I hope you have understood all the 10 questions, very important ones. So practice these questions, practice on your own without looking for explanations or answers, without taking any help. Also set a timer. Okay, start testing yourself. Check your limits. What are your limits? Learn time management. Practice this sum. Set a timer. See how much time you take to solve one sum, and then again do that sum and set yourself a new goal of doing that very same sum in less than the time you took previously. Okay, so this will increase your efficiency, your thinking capacity, your calculation speed, etc. I urge you all to share this particular